Hi, in this mini lecture, we're going to look at one other application of integration, a geometrical one again, like we had with area. And this time we're going to see how we use integration to measure the length of a curve. Okay, so the motivation for using integration to measure the length of curves kind of mirrors that of using integration to define areas. We had a question. I started off this whole topic of integration by asking, what do we mean precisely by area? And we can ask the corresponding question for what precisely do we mean by the length of a curve? So if we have a straight line, we know what that means. If we have a circle, we know how to measure the length of a circle, the circumference. But for less regular kind of curves, we need to be very careful about what precisely we mean by the length of a curve. Now, in practical terms, if we had a curve in front of us and we needed to measure it, well, what we do is, and you may have done this in science experiments or in a practical maths class, we lay out a piece of string along the curve, straighten out the string, and then measure its length. Okay, so in some sense, that's exactly what we're doing here, but using mathematical tools. Because we don't always have access to that curve with the piece of string, because this curve, it might be a hypothetical trajectory in physics, talking about the orbit of a planet around the sun or something like that, or it might be some microscopic strand of DNA where we can't literally lay out a piece of string. Okay, so we'll think carefully about this idea of what do we mean by length and how can we get at it? How can we measure length? So for example, how would we mathematically measure the length of this curve here, whose formula is given in terms of x's and y's? So one thing that we do is, again, as we did with area, we fall back on the idea of using functions. Now, functions, remember, if you give me an x value, I have to give you back a unique y value. And that's not happening here in this diagram, because I can see that x equals 1 gives me, in fact, 3 different y values. But using functions is a really useful thing to do because we have all sorts of useful tools for dealing with functions. So as a first step for measuring the length of a curve like that, the very first thing to do is split it up into sections where we can use functions. So on each of these sections here, coming in from the top left down to the origin and then moving up. So everywhere on that portion of the curve, there is a unique y value for all of the relevant x values. Over onto the second portion of the curve, again, we have the same deal. There's only one y value for every given x value. So there, for example, x equals 1 has just one y value on that section. And then the last section there, same deal. We have just one y value for each given x value. Okay, so the idea there is that for any curve like this, we can always split it up into graphs of functions. So that makes life a whole lot easier than it might otherwise be, because it means that, well, we have those concrete tools of functions and intervals and differentiation and integration and all this kind of stuff that we can use to measure lengths of curves by representing those curves using functions. Okay, so that's our fundamental problem then. How do we measure the length of the graph of some function y equals f of x from x equals a to x equals b? Okay, now I actually have numbers on this example, but the idea is the usual thing. We're interested in the graph of some function y equals f of x between two starting values, x equals a up to x equals b. How do we measure the length of that curve? Well, when we were thinking about area, what we did was introduce a simple way of representing the area under the curve. We approximated it by drawing rectangles. Let's pretend that's a rectangle. So we drew rectangles that touched the curve. And we said, you know what, the area under the graph is more or less equal to the area that I get when I add up the rectangles. We do a similar thing here. And in some sense, it's simpler. What we do is we pick a sequence of points along the curve. We make this, and what we do is we make this chain of straight line segments along the curve from x equals a up to x equals b. And then I think we can see from the diagram that the length of the curve, the actual length of the curving part there that's in blue, if you can see the color, the length of the curve surely must be approximately equal to the sum, remember sigma there, the Greek capital S for sum of the length of the segments. Okay, so this is our key idea, that to get the length of the curve, what we'll do is use lengths of straight line segments. Really important. I don't think I said the word straight yet. Straight line segments. Why do we do that? Well, it gives us a good approximation, as the diagram is kind of showing. And also the really good thing about straight lines is that I know how to calculate their length. That's really easy. Okay, so how would we get a better approximation? Well, the way we'd get a better approximation is we do the same trick that we did when calculating areas. We use shorter subintervals and more segments. Okay, we use more rectangles in the area case. Here we use more of these straight line segments. So rather than having 1, 2, 3, 4, 5 segments, I could use 10 segments. And as you can see, I mean, in fact, even at this scale, it's hard to distinguish the straight line segments from the portion of the curve. So the length of f is really going to be very, very close indeed to the sum of the lengths of these straight line segments. Okay, but let's think now about where these are all coming from. Where are these segments coming from? Well, you can see how I got them. I picked points along the curve, okay, and then just joined them with straight lines. But kind of in the background there, what those points are doing is giving me a partition. Okay, so I'm letting those points divide up the whole interval into these subintervals demarcated by points x1, x2, x3, x4, x5 that give us a partition. Right, so there's something that's shared with integration, and integration is going to sort of magically appear any minute now. Okay, so we're in very much the same territory. By doing this very simple exercise of just putting points on the curve and joining them with straight lines to approximate the length of the curve, that leads us to integration. Okay. So that's one idea that's at play here, is that we're using partitions, we're sampling points, and we're adding up, and we're going to take a limit at some point. The other thing then is to ask ourselves, okay, well, if I take one of those straight line segments, what actually is its length? So here's a zoomed in picture of one of these straight line segments. So it stretches from one point on the graph to another point on the graph. We have these xi values that are coming from the partition. So our x-axis is down below us there. So sorry, maybe I'll just say that I'm zooming in here, in fact, on the graph. So I have my end points of the interval xi minus 1 and xi. And I zoom in on that and just label the important parts here. So the points, there's the x coordinate of this point is xi minus 1, and the y coordinate, well, I'm looking at the graph y equals f of x. So the y coordinate for the I minus 1 point must be f of xi minus 1. And the y coordinate over here must be yi equals f of xi. Now, what's the length of a straight line? Really easy. It's y2 minus square root of x2 minus x1 plus y2 minus y1 squared. Sorry, square root of x2 minus x1 squared. This is the length formula in geometry. Square root of x2 minus x1 squared plus y2 minus y1 squared. Okay, what are the 2 points? There's the 2 points. So that I could think of that as x1, y1. I can think of this point as x2, y2. When I put in all of those values there, I get that formula there for the length of this lad here, this straight line segment from xi minus 1 to xi. Okay, so familiar stuff. It's just the length formula in Euclidean geometry. Okay, so to approximate the length of the curve, I'm going to be adding up formulas like that. Okay, I'm going to be adding up these formulas here for the length of the curve. Okay, let's look at this formula very carefully. What I'm going to do is basically show that this sum is a Riemann sum. Okay, so it needs a little bit of manipulation. Okay, the first step here, what I'm going to do is say that, okay, the square root of a squared plus b squared. What I'm going to do is factorize inside and write a squared plus b squared as 1 plus b squared as a squared times 1 plus b squared over a squared. Okay, so you can verify there, you can verify easily that those two are equal to one another. Sorry, let me just get my bracket right there. Okay, so a squared times 1 plus b squared over a squared gives me a squared plus b squared. And then what I can do is take the a outside, and I'll be left then on the inside with 1 plus b squared over a squared. And of course, you're saying, hold on a minute now, it can't just be a because a might be negative. This should be the absolute value of a. So I'll just note that in this context, the number a is going to be a positive number. Okay, so this square root of a squared plus b squared, there's my a squared, and there's my b squared. We can sort that out using the steps that I've just shown there. And this, why am I doing this? Because it's going to be useful. Okay. So the a in this case is going to be xi minus 1. Okay, and that's definitely positive because in our partition, the xi minus 1 is always to the left of the xi. So that's a positive number. That's my a. And as I say, I'm going to use this little trick here to rewrite that formula for the length. Okay, so there's my a has come outside. So I'm using the end result of that little sidebar calculation, that the square root of a squared plus b squared is a times square root of 1 plus b squared over a squared. Okay, so there's the a. This, the next step then, I use the fact that b squared over a squared is equal to b over a squared. Okay, that's my next line. And I'm going to bring in the usual notation for the length of the ith subinterval. Okay. So there's our formula then for the length of each one of those straight line segments that's cutting across the graph of the function. So the ith one has that length, and it's all in terms of the width of the subinterval and the function values. So I've brought back in the f, just using yi as f of xi and so forth. Okay, now I'm going to look at this, this thing here carefully, this ratio. I'm going to look at this very closely. And I'm going to recall the mean value theorem. Why? Because it turns out to be useful. Okay, what does the mean value theorem tell us? Well, it tells us that when we have the graph of a function, okay, that's, we want it to be continuous and differentiable. If I take any 2 points on the graph, sorry, that's f of b is the y value. Actually, let me get rid of that. Don't need that. The mean value theorem tells us that if we take the, if we look at the straight line there between 2 points on the graph, and we ask what's the slope of that line, well, it turns out that this line has got the same slope as the slope of the tangent to the curve somewhere on the graph. Okay, so what's the slope of that line? Well, that point has coordinates x equals b and y equals f of b. This point here has got coordinates x equals a, y equals f of a. The slope is f of b, y2 minus y1, f of b minus f of a, over x2 minus x1 over b minus a. And this point here, maybe at x equals c, has got slope, that line there, the tangent line has slope f prime c. Right, the mean value theorem tells us that there's always this number c between a and b, where the slope of the tangent matches the slope of the curve, the slope of the straight line cutting across the curve. Okay, so there must be a number, this c number, somewhere between the endpoints of the interval, so that this ratio that popped up a moment ago, there it is, that ratio that pops up in the formula for the length of the curve. It turns out that that quantity, that ratio, is equal to the value of the derivative of f at some point in between from that mean value theorem. So let's have a look now and see what that tells us about the length of the curve. It tells us, the length of the segments that are cutting across the curve. It tells us that the length of the ith segment that we've used to approximate the curve is given by the width of the subinterval times the derivative. Well, this square root 1 plus the square of the derivative. Not the handiest formula, but you know, it's mathematics. It's unavoidable. That's what the formula is. So the length of the ith interval is the square root of 1 plus the square of the derivative of f at some point in between times delta xi times the width of the subinterval. So that's the width of the ith subinterval. Okay. Now we're going to add those up. And remember, the whole idea was that the length of the f of the curve is approximately equal to the length that we get when we add up the length of all of these straight line segments. Okay. So the Li, remember, is the length of the ith segment. When we add up the length of all of the segments, we get a number that's approximately equal to the length of the curve itself. And there's our formula now. We're bringing in the formula that we've just derived using the mean value theorem for that. But what is that? What is this quantity here? Well, it's got a sum. It's got some function evaluated at ci. So it's not f evaluated at ci, but it's the square root of 1 plus the derivative of f squared. And then what do we have here? We have out here the length of subintervals. So we have a sum. We have some function, let's call it g, evaluated at ci's, and we have delta xi's. And that, of course, is a Riemann sum for g. What g? This g. Okay, so that's a Riemann sum for the function square root 1 plus f prime squared, and it gives us this theorem. It gives us this result, that if f is defined on the closed interval AB, and its derivative f prime is continuous, so the usual technicalities, just that are essentially always going to be, well, that are nearly always going to be satisfied for the functions that we'll come across, and essentially always are in applications. So if f is defined, its derivative f prime is continuous, then the length of the graph is given by this integral here. The integral from a to b of the square root of 1 plus the square of the derivative of f. Okay, and it makes you wish that we were still studying areas where we just have to integrate f from a to b. So curiously enough, it just turns out that the formula for length, even though length is somehow more fundamental, is more complicated. Okay. Right, let's have a look at an application. We're simply going to just jump in and calculate the length of this curve here between x equals 0 and x equals 1. Now, if we think carefully about what answer we should get? Well, that's always, I think, worth doing here. And here we should have some reasonably good intuition about what the answer might look like. Because that curve, as we can see, it's sitting below the diagonal on this square. Come on. Sitting below the diagonal on the square. Actually, let me get rid of that. That was horrible. Just try and draw freehand. So we have this straight line diagonal along the square, which would have what length? Well, it would be, our square has dimensions 1 and 1. Okay, just so happens that this function is sitting inside this unit square. So the diagonal of that square would have length equal to square root of 2. And we see the curve then, well, if I get rid of all that extraneous stuff there, the curve therefore should be a little bit longer than the square root of 2, right? Definitely a bit longer than the square root of 2, which is about 1.4, right? But it's not, it should be a good bit away from 2, which would be the length if we went along the perimeter, so 1 and 1 there. So this curve should be a little bit longer than the square root of 2, but certainly less than the length L should be between 1.4 and 2. So that's just kind of a sense check that we can apply to our answer. Okay, but we're just going to make a straight application of this formula here for the length of a curve. See if we can do that integral, evaluate that integral. So let's write down the data that we have. We're looking at the function f of x equal to x to the power of 3 halves. Our left-hand point is a equals 0. Our right-hand point is b equals 1. So we can fill out the different parts of the formula that we need. We need to calculate the derivative. Remember, overall, to integrate, we need this quantity here, square root of 1 plus f prime squared. So we need to calculate f prime. I'm differentiating a function of the form x to the n. So when I differentiate, I get n times x to the n minus 1. N in this case here is 3 over 2. So there's my derivative. F prime is 3 over 2 times x to the power of a half. F prime squared, f prime x squared there will be what? 3 over 2 times 3 over 2 is 9 over 4. And x to the half times x to the half will be just x to the power of 1. Okay, so we can write down that the length of f is the integral from 0 to 1 of the square root of 1 plus 3 over 2 x to the half squared, which I just did a second ago. So that'll be the integral from 0 to 1 of 1 plus 9 over 4 times x dx. Okay, so with this integral to calculate now, and the way we can calculate that, the way we can evaluate that integral is by making the substitution u is 1 plus 9 over 4 x. So I have this from the techniques of integration. What do I need to do there? I need to calculate the derivative. So I could say that here du dx is 9 over 4. We have just that linear function. So I see that du is 9 over 4 times dx, or the other way around, dx is 4 over 9 times du. So I can make that substitution for dx. The square root of 1 plus 9 over 4x, well, that's just the square root of u, or u to the power of a half. And the limits when x equals 0, that gives me that u is equal to 1. Okay, there's my connection between x and u. And when x equals 1, I get u is 1 plus 9 over 4. What's that? 13 over 4. Okay, so I make all those substitutions, and I end up with a relatively straightforward integral to do. The integral from 0 to 1 turns into the integral from 1 to 13 over 4, u to the power of 1/2, and dx is 4 over 9 times du. Okay, so fundamentally, the antiderivative that I have to calculate is u to the power of a half du, and I have some constants knocking around that I need to take care of. Okay, so that should be enough to enable you to fill in the little gaps there and come up with this result for the integral. Okay, using the substitution that I mentioned there. So just check the numbers yourself here. We want to put in our limits x equals 1 and x equals 0. So I have 8 over 27, then put in x equals 1. I get 1 plus 9 over 4 to the 3 halves. Put in x equals 0. I just get here, so that's 1 plus 9 over 4 times 0, which of course is 1 to the power of 3 halves. Tidy that up, chuck it into the calculator, and sure enough, I get 1.4397, which, as I said, when we had the sort of sense check, it should be a little bit bigger than the square root of 2, which is 1.41, blah, blah, blah. So checks out. Okay, so the key thing here really is to be able to apply that formula for the length of a curve. But it's important to look at the background to see where this formula comes from. It doesn't just drop out of the sky. It comes from using the maths about just the length formula for a straight line, using Riemann sums, and using that mean value theorem, which is important at that crucial stage that we just saw there. Okay, so that's the end of this content on the applications of integration, sort of linked by a geometric theme. We looked at areas, we looked at lengths, and we looked at this idea of the average of the function. So make sure to do the loop quiz to ensure that you've got to grips with the key things here, and then move on to the problem set where you practice all this material.